Good evening, everyone. Welcome back to NPTEL live session for week 6. And we will be discussing today about protein structures, primary, secondary, tertiary, and quaternary. Along with that, we will be talking about how the CD spectra depends upon pH and temperature, and what is the difference in alpha helix, beta sheet, and tandem coil structures in different various examples, how CD spectroscopy helps in understanding the structures as well as identifying different secondary structures. So we will shortly start our session. Uh, we right now we are waiting for a few more minutes for others to join. The topic that we will be covering today, I will just write it down over here. We will be talking about tertiary and structures. You can name them as primary, secondary, tertiary, and quaternary, followed by a detailed discussion about alpha helix, beta sheet, and random coil. Then certain spectroscopy which can be used to identify the structures of these three different forms of proteins. And lastly, the factors on which CD spectra for these secondary structures would vary. So these would be the four main topics, and at last we'll be having our assignment questions, which would help you to solve or at least to do a given approach for solving the problems that have actually been given in the assignment. Besides this, if there is any other doubt or question regarding the sessions that we have taken so far, I'll be happy to answer that. Please feel free to put your question in the chat box or unmute yourself and ask it at any point of time. So we can start now. As we already know that proteins are being made from amino acids. So the polymers of amino acids are basically the protein. The proteins are basically the polymers of amino acids. And we have talked about 20 amino acids, all aliphatic, aromatic, polar amino acids containing S, sulfur or selenium, basic and acidic amino acid, and one secondary amino acid which is proline, and so on and so forth. So we have talked about this in detail in our previous session. So what are basically we are trying to understand over here that if we are saying that it is a polymer of amino acids, polymer looks like this way, where we have a certain chain. So this is one protein, amino acid, and this amino acid will combine with another amino acid, where I'm talking about the R2 group and R1 group. This is alpha amino acids we are talking about, and COOH, since it would undergo a condensation where we will be having loss of water molecule. So, so after this one, we will be having C double bond O, NH, Cr2, H, and COH. So this is one certain chain which is having two units, and this is what we call as a peptide linkage. This is basically an amide linkage. So based on that only, how our structures look like in the proteins and what is made up of, we have classification of proteins on their structures. First is primary protein structures. So here it is basically just a combination of all the amino acids in a linear fashion. So we will be having, say for example, I'm taking code which is GAV, and this is a protein which is comprising of glycine, alanine, and valine. So it is basically a very simple linear chain of the proteins, amino acids, sorry. Whereas if we talk about the secondary structure, this is further classified into three types. First is alpha helix, second is beta sheet, third is the random point. So talking about alpha helix, so alpha helix is also, if we consider this protein, so here basically in this structure we talk about the interactions of CO group with the NH group of the other moiety. So it is having, since out of carbon and oxygen is more electronegative. So the charge density would be onto the oxygen. And here we would be having a positive charge on nitrogen. So this polarity, actually the CO group of one amide we are talking about, not the amino acid, amide group. Once this protein linear chain has been formed, that interacts with the NH group of other amide present in that particular chain. So it could be through hydrogen bonding or some electrostatic interactions. For example, we have this helical sheet, and here we are having C double bond O, and in this one, the amide group NH. So it is basically having an hydrogen bonding interaction. So that makes the alpha helix structure of the proteins. So generally, when we have a linear chain of different amino acids, they would give a primary protein structure. And when those primary protein structures are starting to have the interactions, say carbonyl group of one amide is interacting with another hydrogen of amide group, NH group of the other amide present in the same protein. So that would give rise to a certain kind of interaction, that is a hydrogen bonding interaction, and that would rise to alpha helix structure. Similarly, we have the beta sheet, the second form. So this is basically intramolecular, where within the system it is happening. So in the same system it is happening, whereas beta sheet, it would happen between the different chains. So here, different chains or interactions we observe chains interaction. Say for example, we have C double bond O group here and NH group here, and this NH group is further connected to C double bond O, that amide ring and the R, right? And similarly, we have the other side, the second chain, NH group, and here it would be C double bond O group, and then NH, then R, and C double bond O. So and so forth. So here, if you will see the interaction between oxygen, CO2 and NH of the opposite or the interchains, that would rise to a beta structure. So if you will see here, it is oxygen, here it is NH. So it is basically a anti-parallel system where it would go like the opposite direction. In other case, if we have both the moieties at the similar fashion, if both the molecules are oriented at the similar fashion, say we have, I'm taking NH, and similarly we have here NH. And now the interactions are going to happen. So this moiety and this moiety, they are facing each other in a similar fashion. And here we have a hydrogen bond interactions. So this is called when both the systems are parallel to each other, both the chains are parallel to each other, and the interaction is happening. That would give rise to a beta sheet. So different chains are involved, whereas in alpha case, the intra hydrogen bonding interactions happen between the carbonyl group and the amide group. Followed by we have the third structure, which is the random coil. The random coil also has hydrogen bonding interactions, but as it is named, it is randomly oriented, so it is not following a particular fashion. So there is no proper arrangement, no particular fashion is being followed. It's randomly oriented, and we will have a hydrogen bonding randomly. That's why it is called as random coil. So it is not having a perfect structure. Coming to our next classification, so we are done with primary and secondary. Now it's tertiary structure. So basically, this is a combination of both alpha helix and beta sheet. When we are talking about the primary, secondary, and the tertiary, so we have discussed that in primary structure, we are just having the linear chains of amino acids, which would give you the interactions. So, for example, you have this particular code. Each code would define a particular amino acid, which has been discussed earlier. So G stands for glycine, G stands for alanine, and D stands for valine. Different R groups onto the alpha amino acid. When there is interaction in the amino acid chains, that leads to secondary structures, and we have three different types of secondary structures. One is alpha helix, second is beta sheet, third one is random coil. So depending upon the interactions in intra or interchains and whether they are being defined or not, we have different structures. So taking alpha helix into picture, so for example, this is a linear chain where we have different amino acids. So this is one group which is combined with another group, and so on and so forth. So this dash represents a n number of chain. So if you will see that this particular peptide bond or amide linkage, so here we have a charge distribution where carbonyl oxygen is having the negative charge density, whereas the amide NH is having the positive charge density. So when we have one CO group, if you consider this particular structure of protein, so one CO group having the negative charge density can attract or interact with the proton of your NH of the second amino acid. If it is happening in the similar chain, one single chain, it is happening, that is intra chain, it is working as hydrogen bonding interactions, that would give you a alpha helix structure. So nothing is working in between the two chains. Whereas if you have different chains, say for example, this is one chain and this is a second chain which has been drawn in blue color. And if you see the carbonyl oxygen is interacting with the hydrogen proton of the NH of the second chain, so it is no longer an intra, it becomes an inter. That means two different chains are involved. Similarly, the NH of the same chain is interacting with the carbonyl of the other chain through hydrogen bonding. So this is called as, this would give rise to a beta sheet structure. Since the oxygen is interacting with NH and then NH is interacting with oxygen, so this kind of formatting leads to an anti-parallel structure. Whereas if the similar groups are at the similar side, say carbonyl group is heading towards this side, the other carbonyl group of the other chain is also heading towards the same side, and still they are having a hydrogen bonding interaction that would lead to a parallel beta sheet structure. Followed by the third type of the secondary structure was random coil. It is also having hydrogen bonding interactions just like alpha helix as well as a beta sheet, but as its name suggests that it is randomly oriented. In this case, we can see that it is particularly at every step you will get a hydrogen bonding because you are having a carbon and an NH facing towards each other. Whereas in random coil, the structure would be like there is no particular structure. You cannot name the structure. It is randomly oriented. So it is called as a coil only. And followed by the third classification of the protein structure is tertiary structure, which is having a combination of both alpha helix as well as a beta sheet. So this particular structure would be having the units of alpha helix as well as the beta sheet. Followed by our last and fourth type is quaternary protein structure. In quaternary protein structures, so this is, as we said, that tertiary was having both alpha and beta, and quaternary is also having the alpha and beta, but it is being classified that it is having different subunits which are comprising of the tertiary structure. Say, for example, if we consider this block where we are having four different subunits. So this is well defined, and this subunit are nothing but a combination of the tertiary structure. And we know that tertiary structure are nothing but a combination of alpha helix and beta sheet. So, for example, if we consider hemoglobin, so hemoglobin is actually a quaternary protein structure which has four subunits, and those subunits are comprising of two alpha helix plus two beta sheet. So here, if I'll just say that this is the shaded pink shaded one is the beta sheet, and the blue shaded one is our alpha helix. So the combination of alpha helix and beta sheet, that means a three tertiary structure, and giving in a subunits form that would give rise to a quaternary protein structure. So this was about the different structures that we are having for proteins. We talked about the primary, secondary, tertiary, and quaternary. We've already discussed about the amino acids in our previous session. So if there is any question, you can just put your question in the chat box or unmute yourself and uh, ask before we move to next. Okay, so if there is no question, so we can just move towards our next topic. So these were the topics that we are going to talk about. So we have already discussed just now what are the four different structures, and now we will be talking about. We have also discussed about the alpha helix, beta sheet, and random coil. Now, the main part of the discussion of today's discussion is that how do we find out, which is very important. How do we find out the protein structure? So we saw the different types, and basically the tertiary and quaternary, they are composed of the secondary structure itself. So we mainly target to identify the secondary structures because it is having three different types. So how do we do that? Generally, we know that one particular spectroscopy or the analytical tool that we have in hand is the X-ray crystal structure, the diffraction. So how does it work? Just a basic principle. So if we have in different planes the atoms, I'm just taking a normal example, and here when we pass the X-rays, They would strike your atoms at a particular plane and then reflect back. So it would form a diffraction pattern. And wherever you have bright spots, that combination or the superposition of those things, and when they are in phase, and you will get a particular crystal structure. You get a structure over here, and you can identify, okay, you have a carbonyl group over here and NH bound to it, or so and so. But in this particular situation, we need to know that it is very difficult to identify the protein structure by using the X-ray, because the side chains, whatever it would be having, they would be randomly oriented. And if we say that random coils, they don't have a structure really. So they are so flexible, they can move at any point of time, and we won't be having the X-ray structure. Also, proteins do change their structures. They can have different structures in solution also, starting with the random coil, say for example, and it would be in equilibrium with the beta sheet, say for example, this beta sheet, and it would be in equilibrium with your alpha helix also. So when the equilibrium between three different forms are existing at the same time, because of the thermodynamic stability of those structures, we can't really see the extra structure, because for the extra structure, one structure needs to be identified and the diffraction pattern has to be formed. If it's a combination of all the three, we won't be able to see any pattern over there. So what is the solution for it? So we got to know that X-ray structure, crystal structure can't be the solution because of the randomness, as well as like thermodynamical equilibrium between the random coil, alpha helix, and the beta sheet. So when something is continuously changing its structure, we can't really identify the structure, crystal structure of it. So what is the solution? So here comes the topic of your course, which is the CD spectroscopy, circular dichroism spectroscopy, which we have already discussed in the last session. What is CD spectroscopy? So CD spectroscopy, basically, we have already seen that CD, which is circular dichroism. So this is the motion that we are talking about, like it goes in a circular motion. Di means two, and chroism means two, means colors, or colors are referred to the absorbance. So this one particular wavelength absorbance would give you one particular color. So this circular dichroism, that would really help to identify alpha helix, beta sheet, and random coil. How? We will just check it out now. In circular dichroism, what we saw that all the three are having, so in CD spectra, all the three, that is alpha helix, beta sheet, and the random coil, they have their own signatures, which can be easily identified. So how does it look like? I'll just show you now. So if we consider this is our positive and minus, we know that it is being represented by psi, and here would be our wavelength, and here the how it is going to look like. So firstly, in alpha helix, we generally have, starting from the positive electricity, giving two bands and staying in the negative region. Then when we have random coil also starting from the positive region, but would give only one maxima here, and then going to the beta negative, or coming back to zero. And the random coil is having a totally different signature, which starts from the negative end, giving a minimum depth, and then coming at a zero. So if you will clearly see over here, so this is your random coil in green. This is your beta sheet, and this one is your alpha helix. So if in any structure of protein, we are having alpha helix or beta sheet or a combination of all the three, we will be able to see or identify based on the different absorbances they are having. So it would be very easy to identify which structure they are particular, what is the sequence of it and how they are actually oriented. Now, if you really need to identify, there are certain values which are fixed for alpha helix, beta sheet, as well as random coil. So in alpha helix, these are the important points. In alpha helix, we generally see in CD spectroscopy these certain points. Point one is it would always be having as a positive band or a signal around 190 nanometer. So these values are more or less fixed for all the alpha helix because this is not going to change. It is irrespective of what amino acid you are taking. The values could be 10 plus minus 10 shift, but it would be definitely starting from a positive end, not from a negative end, and the range would be around 190 to 200. Second point for the alpha helix is it would always show two negative signals at absorbance 208 nanometer and 222 nanometer. So this is very, very strong absorbance and this can be easily seen. So it's very strong. It is having very high intensity. So it can be easily seen in the CD spectrum. So if, as I mentioned over here, if it is having 190 one band, other band at 208, this is 190, this is 208, and this is 222 nanometer. That is called as your alpha helix. So this is very easy for to identify alpha helix, beta sheet, or random point. Now the second signature that we are going to talk about is of beta sheet. So beta sheet also, as we saw, that it also starts from the positive end only. So it will show positive band at 195, which is very close to your alpha helix. But in the negative region, it would only show one band in negative region. So this negative region becomes more of more importance because in alpha helix you see two negative regions that two are 280 222. But in the middle of the two, if you see any negative signature on that only one band, that is of your beta sheet. So this is also clear. Moving towards our third, which is the random coil. So random coil, as we said, that it is randomly oriented. And this is having typically a different signature from both of them because it starts with the negative end. So starts with negative signal. Even if you don't see the value, and if the spectra is starting with the negative signal, that means it is symbolizing your random coil. So this also ranges at 195 states. Now, if we compare the beta sheet and the random coil, both starts at 195 nanometer, but their sign would be different. One is having positive sign and other is having negative sign. The negative side refer to the random coil and the positives refer to the beta sheet. And this also has in positive region a very broad signal around 210 to 230 nanometer. So all these particular structures would be easily defined by their absorbances and the pattern. So as we said that this is your 195 and this is your 195, but this is negative, this is positive, and this is for the random coil. And the broad thing that is going to come that is in between that range, 110 and 230. Similarly, in beta sheet, we only see a signal at 218. So this is where we can easily find out with the help of the CD spectroscopy. Now, why these particular values? Why are we not talking about 100 nanometer or 400 nanometers? Why are we specifically talking about 190, 208, 220, or this particular range? So for that, we need to understand from where these values are coming into picture. So the next question that we have here is why these signals appear at particular wave numbers or wavelength. So basically to answer this, we need to understand that how the protein structure looks like. So it is a chain of amino acid. Say this is one amino acid combined with your second amino acid and so on and so forth. So this is your end chain. So if you will see over here, what are the functional groups that we are talking about? The functional group is nothing but your this region, the amide region, that is your functional group. And the other functional group could be your R. If it is phenyl, in case of the phenylalanine, then it would go to show 260 to 270 nanometer. That is the UV range for it. Similarly, if we have tryptophan, where we have a benzene ring induced with the this indole ring, so this tryptophan would give you around 28 nanometer. So this is one set. But besides that, we have this very important functional group, which is the amide functional group. And here, when we see the kind of interactions it is having, so we know that these kind of moiety, which is having a lone pair and a double bond, it shows N to pi star going from your nitrogen end to the carbonyl pi star. So this happened from the lone pair of nitrogen to the pi star of your carbonyl group because it's a pi acceptor. Whereas the second is your pi to pi star, where this double bond goes to the oxygen. So this pi to pi star coming from this particular region. So the range of N to pi star is basically 210 to 230 nanometer. And pi to pi star is from 180 to 200 nanometer. So that is why when we said alpha helix, beta sheet, and the random coil, all three of them were having one signal specifically at 110, 190, 195, and 195 region. This was in positive, this was in negative, and this was also in positive. So this is because of your pi to pi star. Whereas the 210 to 230, we already defined that 218 would define for the beta sheet and 208 to 222 for the alpha helix, and similarly 222 or something like that for the random coil of broad region. So that is why these particular values are there for alpha helix, beta sheet, and random coil. It's not just any from anywhere we got these values. There is a specific definition for this value. Why it is coming? Because of the amide linkages that we are having. That amide C bond O and NH groups, they are having N to pi star transition and pi to pi star transition. Because of that, they absorb a certain wavelength, and therefore we could see a signal at that particular wave. I hope this is clear. If not, please feel free to ask before we move to the next topic. So is there any question so far? Okay, so if not, as I said that we completed the spectroscopy part also, how we can define it, and also from where those wave numbers are coming into picture. Now, the last topic of our today's discussion is what are the factors on which the CD spectroscopy depends? So, there are two factors, majorly two factors, that affect the spectra, CD spectra. One is your effect of pH, and second is the effect of temperature. So, in case of pH, or firstly, yeah, we'll take the first part, which is the effect of pH. In case of the pH, generally, if we take a normal optical spectroscopy, we won't be able to see any difference in the optical spectra, or absorbance data won't be giving you any much information regarding the pH or the different temperature. Say, for example, if we are drawing, so if I have this normal absorbance spectroscopy, the epsilon, and if I am making, this is one, we know that how the UV spectra looks like, or the absorbance rate or optical spectra looks like. So this is our, this is the second piece, and then this is the third piece. So while I have drawn the three things, so if I am saying that this is of beta sheet at pH 10.8 and 52 degrees Celsius, defining both pH and temperature. And if I'll say that this orange trace is of random coil, having said that pH at 6 and 25 degrees, that means room temperature. And the last one, if I'm saying that this is my alpha helix at pH 10.8, but at room temperature. So if we see carefully this absorbance data, we don't really see any kind of shift. Even if the shift in the beta and random coil we can identify, but in alpha and beta, there is only an intensity difference. We don't really see a particular shift. So the optical spectra does not give complete information. So that's why CD spectrum becomes very, very important in that case. So how your CD spectra would look like. We know that this is a 0, this is positive, this is negative, and we're talking about the molar ellipticity side, and here it would be your wave number. So in case of, when we said that alpha helix is there, so it should be having a band at 193 or 195 going to this. So this is at 193 nanometer. This is at 208 nanometer. This is 222 nanometer. Now for the beta one, we will be having around the similar region, but with a little shift and going to a broad region. So this is around 195 nanometer, and this is around 218 nanometer. And the last one that we have is starting from the and going to negative, very broad. So 195 nanometer, and this is also around 222 something. So the blue one is alpha helix, the red one is beta sheet, and the green one is random. So this is basically at different temperatures as well as in pH also. So at pH, at pH equals to 6 and temperature, I'm writing it as capital T for spacing 25 degrees, that is at room temperature, we will only see the random point starting from the negative region. So I have drawn everything over here. At pH 10, when it is basic, 10.8, and temperature is room, that is 25 degrees, we see alpha helix only. So drawn in blue color. Whereas when the pH is 10.8, that is basic, but the temperature is higher, which is 52 degrees Celsius, it would give you a beta sheet, which is the two bands. So this gives you a clear-cut idea that at different pH and the different temperatures, how your spectra is changing because of the change in your structures, which was not possible in case of the optical spectra. So this is how CD spectroscopy helps clearly to identify that how the pH temperature really affects your structure and which structure now it is having. Say, for example, to be more precise, that protein at pH equals to 5.9 going to pH equals to 12. So this is nearly neutral, closer to uh, closer to 7. So it would definitely be giving you a random coil structure. So when it goes to pH 12, so this becomes basic in nature, and we get sometimes a mixture of both alpha helix and beta sheet. But this can be easily seen that how with different pH, how we are, what we are expecting, and how we are able to identify it. Also, one announcement that this meeting is going to finish in 10 minutes. So please rejoin the same link for continuation of the lecture. Thank you. Now, coming to the temperatures, the effect of temperature. So when we see the at different temperatures, say for example, we have this alpha coil and here we have a beta. Okay, so this is your psi and this was your wavelength. So now what I'm saying that this is the alpha helix. But if I redraw this one, so this I'm saying it's a mixture of both alpha and beta sheet, alpha helix and beta sheet, but beta sheet is majority. So in that case, we can easily plot between delta ellipticity because we know that psi is dependent on the ellipticity and with respect to the temperature. So for this particular point, we will be able to see that how we get a sigmoidal curve. So if we are having this at room temperature 298 Kelvin, and this is the temperature which is your melting, where your melting of the molecule starts. Okay, so this one, so we have taken two different temperatures, and in the middle of this one, where your temperature, where your structure actually breaks to form another structure. So this is called your melting point. or the melting curve. So you can easily see in if in this particular structure you're getting a peak at 195, also one peak at 208, similar to that of your positive alpha helix, but a broader peak again here at somewhere at 222, not reaching to 230. That could also be a possibility of having a mixture of alpha helix and beta sheet, which we can easily define from the series spectrum. So this is how we can see the effect of pH and temperature on the series spectra for different structures, alpha helix, beta sheet, and random point, where we need to identify the pattern, the signals at what wave numbers, and whether it is starting from the positive end or the negative end. So uh, I'll just give again a small brief that we have taken so far before going to the question. So So today's discussion was totally about the different forms of the structures of the protein, starting with the definition of the protein in a simple layman language, that it's a polymer of amino acids. Polymer means the combination of monomeric units, like small units which are being combined together to condensation. And amino acids we have already talked about, like we generally talk about the alpha amino acids, which are 20 number, and there are different types: aliphatic, aromatic, polar, basic, acidic, having sulfur or selenium, or the secondary amino acid, which is sodium. So this particular classification with their one single letter code or three letter codes, and what are their advantages, that we have already discussed in details in the previous sessions. You can go back and watch the YouTube video. So here what our basic purpose was, that how the protein is being formed. As you can see, the carboxylic group of one amino acid, that is monomeric unit, it is getting condensed with the amine group of the other monomeric unit, giving rise to a peptide amide kind of linkage where we have a pseudo bond of NH. And now the classification based on the structures and how that it looks like. So in primary protein structure, it's just a linear chain of all the amino acids combined or condensed together, where if I say that GAV, define this particular protein, it is composed of glycine, alanine, and valine. So it's a linear form. We are not talking about any kind of interactions over here. But in case of the secondary structure, we do see the interactions, majorly the hydrogen bonding interactions, where we have the alpha helix, beta sheet, and random coil. So in alpha helix, if we take the similar single chain and we distribute the charge over the carbonyl group and the NH group, carbonyl group would be having negative charge density compared to the amine group. And if in the single chain, if we have this particular structure in the single chain, we have the carbonyl group interacting with the amine group of the other amino acid, but in the similar chain through hydrogen bonding, that would give rise to a alpha helix structure. Whereas if we have different chains, like more than one chain, and there is a hydrogen bonding interaction, be it parallel or antiparallel, that would give rise to a beta sheet, and it would be having a defined structure. Whereas having hydrogen bonding interactions between different chains, but randomly oriented, that would give rise to a random coil. And tertiary structure is combination of both alpha helix as well as the beta sheet. And the quaternary structure is having the subunits, which are comprising of the tertiary structure, which is nothing but your alpha helix and beta sheet. Where we have taken example of hemoglobin having four subunits comprised of two alpha helix and two beta sheet. Kindly rejoin the same link